Okay, welcome to another short OpenStack astronomy. Here we're going to be starting our module 3, which will be looking at stars. And so we're going to first start off by looking at one star we're very familiar with, our own star, the sun. And so we'll start off with the structure, composition of the sun, what we know. And then afterwards, we'll kind of infer this stuff to other stars. So here's just some kind of specs for the sun here. Earth across. Now the Earth is here in this image just as a reference. We're not actually that close, but this is to scale in terms of size. And so you could fit about over 100 Earths across side to side. For the sun, about 109 Earths across. Surface temperature, and we talk about temperature on the surface on the corona, and I'm sorry, the photosphere, which is about 5,800 degrees Kelvin. Now, Kelvin's going to be a new measure of unit. It's very similar to Celsius, off by about a few hundred degrees. But if you want to get kind of a comparison to it with Fahrenheit here, we could kind of see that it's slightly double. So the core temperature inside is 15 million degrees Kelvin. And if we talk about it in Fahrenheit, that's about 27 million degrees Fahrenheit. So Fahrenheit is a little less than double the conversion factor, but our temperatures are going to be very high, so that's going to kind of be a nice ballpark where you could kind of do that conversion there. So look at the difference though in the core, right? We're talking about millions of degrees versus the surface temperature, which is only about close to 6,000 degrees. So very, very different temperatures there. And then, of course, luminosity measured in watts there. And then masses. Over 300,000 Earth masses would be equivalent to that of the sun. Here's the sun's structure. If we kind of opened it up, looked at the interior here. The core, this is where nuclear fusion is generated. Again, 15 million degrees Kelvin there. Then you have the radiation zone, where that energy is transported upwards. And then a convection zone, so very similar to that of Earth, where you have that rising hot gases that go up, then cooler ones come back down. And then what we consider the photosphere, which is the surface. And that's at about 6,000 degrees Kelvin, 5,800 actually. Now, the sun doesn't have an actual hard surface. It's more kind of a plasma. So the layers kind of merge and mash up together there. But the photosphere is what we consider the surface of it. And then you have kind of the atmosphere, has kind of a few layers there. So the chromosphere, which is that middle layer of the atmosphere there, and then the corona. And notice that those temperatures spike back up right around there. And then, of course, we have the solar winds, which is those charged particles that tend to flow outwards. Here's an image kind of the atmosphere, the surrounding the corona here. Notice that the sun is blocked out in the center, and typically during a solar eclipse, we're able to do this so we don't get bombarded by that visual light. It's really one of the only times we're able to see the halo right around the edge. And so during those eclipses, we're able to see a lot of information about some of those outer layers. And here's an image of the temperatures in the atmosphere. So again, the corona down to the chromosphere, and then the photosphere, which again is the lower level of the atmosphere, or we consider the surface there. And so the temperatures drop, and then they spike back up as they go towards the core. So the photosphere is really the coolest region of the sun's layers. Here's an image, just kind of a collage. So the chromosphere, the photosphere, and again, that photosphere being the surface, we could see some sunspots there. And then you could see that the corona really extends outwards there beyond the surface there. So a lot of activity there. And then down at the bottom, what we call the corona hole there. And we see a lot of activity there as well. Down here, we could see the corona hole in the bottom, and we could see a lot of electromagnetism, a lot of activity there in that darker region down below. And so also, again, along the surface there, you see kind of that haze, right, in the corona all around. You could kind of see a lot of these solar flares, prominences, a lot of activity happening on the surface. As Galileo had viewed, right, the sun is not a perfect sphere, but it is kind of changing, right? We see the surface moving around. Here's an image of the photosphere, and we could see these, excuse me, these sunspots. And the Earth is there just as a reference to kind of get a sense of scale. So these sunspots are extremely large. They're kind of Earth size. And these are typically some cooler regions where the gases are retracting inwards into that convection zone. And so these sunspots here are these kind of regions where the gas tends to come back down, cooling off, and then that gas goes up. So in that convection, right, we have that energy cycle there. And it kind of looks like granules of like a corn or so if you look at them closely there. But this bottom right is an actual image of the surface of the sun there. And we could see, right, those edges there, kind of the borderlines, darker parts are those gases that are going down. And those wider bright spots are the gases coming up. So we see that convection cycle happening here. So let's talk about the solar cycle a little bit. What type of activity happens on the surface of the sun or stars? And we are interested in the surface, the activity, because here on a planet, right, that's really what we consider weather, what's happening on the surface there, the activity. So we see a lot of sunspots as the sun rotates. These sunspots also tend to migrate, so they move along. They move along, and again they flare up. A lot of them have these mass ejections here as well. And so when we look at them and we look at these emission spectrums, what we see is this Zeeman effect on the sunspots. So when we look at those absorption lines, what we see is that they tend to swell up or get a little bit wider. And so this happens whenever there's a high magnetic field. So we see that these sunspots have a large magnetic field associated with them. So the sun has a magnetic field. As it rotates, those magnetic field lines tend to kind of swirl around. And what we see is those sunspots that we found them kind of migrating, moving around, will tend to follow along those magnetic field lines. So think of them as kind of highways, and the sunspots will migrate along them. So they move along those. They're charged particles, they are attracted to them, and so we see that electromagnetism is really driving those sunspots. And here's kind of a collage, an image looking at this magnetic kind of activity that we see of the sun on the right, and we see that there's a cycle. So a lot of activity on that first kind of image, and as it goes towards the back, you see less activity and then coming back again. So there tends to be a cycle of this magnetism, right, that peaks and drops down. Here's some more images, just kind of plagues on the sun here. And so with the spectral lines, we see kind of these ionized calcium there. So we see that there's also some activity here beyond the surface, right? Beyond the photosphere. And let's take a peek at what exactly that is. So we see a lot of magnetic activity that will create these solar prominences. So here on the top left of the image, you see these flares that are going up extremely, extremely large there above the surface. And so what we see is that sunspots, since they have those magnetic fields, they will end up making a magnetic kind of highway between them. So they'll make this magnetic field between two sunspots, and it will trap these gases. And so you have all of these, these charged particles that will tend to travel along there. So you'll get these large flare-ups that are driven by the sunspots, but they'll extend way beyond the surface. And so here on the top left, you can see one of those prominences, extremely large. Again, the Earth is not that close, but just there for scale reference. So you could see how large these flares actually go. And on the right is just a collage of different prominences, again, not happening at the same time, but you could see the activity there extremely large. So these magnetic fields get very large. The activity, these particles very charged, and draws out these flares. Here's a coronal mass ejection here, a burst of those charged particles. And these are very violent, right? They will go throughout the solar system. So these are, again, creating, discharge with the solar winds. They create some radiation there. But just amazing that we have an image with such clarity here to actually be able to see one of these mass ejections. Here's another image of a solar flare, again, sending out those X-rays, those charged particles. And you could see here a bit more of the surface there, looking like that plasma type material. Again, not a solid surface there. And here we have a kind of a collage of, images in different wavelengths here. So visual light, I believe it's probably one is X-ray or ultraviolet here. But you could see that with in visual light, we don't really see a lot of the activity beyond the surface there, but we could actually see that with other wavelengths there. And we see there's a lot more activity happening way beyond that surface. And so what we find is this solar cycle, when we track the activity here, we see that there is this 11-year cycle of when there are mass flare-ups and then when it calms down. So there's an 11-year cycle when you have a lot of this magnetism, a lot of these prominences, flares, sunspots. So here's an image on top here with sunspots, and then here at the bottom is kind of the latitude of them. And so you could see when they peak, you have a lot of them, and then they will start to migrate towards the equator. Again, following those electromagnetic kind of lines that as the sun rotates, it creates those magnetic fields there. And so we see that these peaks happen roughly about every 11 years. So that magnetism, the sunspots are connected. And that's the activity happening on the surface, which is what we consider weather. So the sun is always radiating these particles. although the sun gives us life, it is also very, these particles are very hazardous to us. And so our own Earth has a magnetic field that deflects most of them. And if some actually do come in contact with our magnetic field, they will typically travel and go in on the north and south poles, which create the auroras, which is just kind of those viewing those charged particles in the sky. And so this cycle happens every 11 years. There is a peak of these in outbursts. And so for communications, perhaps satellites that are out in space, you get a lot of these particles that could be very damaging. They could also affect electric grids, causing blackouts. And so we get this surge of them about every 11 years or so. And so something to consider, as since we're highly dependent on satellites and these electric fields, right, to power, cities, hospitals. And so here's an image of the auroras. So those charged particles leaving the sun, then hitting the magnetic field of the Earth and coming in on the poles there. And so they create these amazing light shows and you could kind of see these fluorescent colors through the sky.